All right, now welcome back. Today we're going to have a look at a square root function, which is built off the back of a parabola. And I know all of you just groaned inwardly, but bear with me. So, first of all, you have your normal parabola, which looks like this. And this equation is y equals x squared. To turn it over, you make it y equals negative x squared. And I'm showing you that so that you can get some context for the next step. So a square root function is actually part, or most of it, looks like this, all right? And this function here, the whole red thing, is a sideways parabola. So we know how to turn a parabola upside down. We don't know how to turn it sideways. Some of you have seen it before in one of the parabola sets, but just to remind you, the way to turn a function sideways is to swap the x and the y and rewrite it like that. So it becomes x equals y squared. Now, we don't normally work like that. We work as y equals. Otherwise, we don't have a way of graphing. See, this one here, this is still the independent variable. But what you're having to do is work out what y is, then square it, and that tells you what x is. So we need to rearrange this to become y equals. So your first step is to square root both sides. So you have y now equals the square root of x. And look, this is called a square root function, and all of a sudden a square root has appeared. But you'll say to yourself, hold on a second, a square root, when you square root something, you must remember that it has two solutions. So this has a positive square root of x and the negative square root of x. So now look back at your graph. I'll show you. Here is the positive solution. So these are all positive values. And the lower arm is your negative solutions. So this sideways parabola of x equals y squared was made up of two different square root functions. It was made up of y equals plus root x and y equals minus root x. So this is the basic form of a square root function. You've got either this one, which is above the x-axis, or you've got this one, which is below the x-axis, like so. Just to make it clearer. There. And we put this on. Now, a few features, all right? A few features of a square root function. The basic one always starts at 0, 0. All right? Because if you substitute 0 in place of x, the square root of 0 is just 0. It doesn't matter if it's negative or positive, it's always 0, 0, so long as there's no translations in it. All right? Another key point to remember for the basic one is when x equals 1, the answer is still 1. So that this one here, it goes through 1, 1. And the same for this one, just negative. So it goes through 1, negative 1. All right. You might see some symmetry as you go through and put x equals 4 in. The answer is 2. And for the negative root x, the answer is negative 2. So you can see some symmetry above and below, the same as for a parabola, which had symmetry across the y-axis. The sideways parabola, or the two halves of the square root function, have symmetry across the x-axis. All right, so that's a good thing to remember. Imagine the x-axis is acting as a bit of a mirror in the middle there. All right, so moving on a little bit further, would it surprise anyone to learn that we use the exact same variables to show horizontal and vertical translation? So we've got ourselves inside here is h to show horizontal translation. Outside the square root is k to show vertical translation. And leaving myself just enough space, outside the square root at the front multiplied to it is the a value to show dilation. All right, so just to reiterate, this is horizontal translation. This one is vertical translation, and this one is dilation. All right, now, if you remember from the previous example, this dilation can be a little bit tricky to work with. What you want to remember is that it stretches a graph, whereas the h and k values physically shift it. I don't know if that makes sense to everyone, but that's the way I like to think about it. Dilation is, imagine someone grabbing hold of this arrow here and pushing or pulling while keeping the 0, 0 point anchored, whereas the vertical and horizontal translation, the entire thing is open or able to move up and down or left and right. So just keep that in mind. All right, so I've just brought up a Desmos screen and we're going to have a bit of a play around with a table of values to explain the dilation factor, because it's the most common thing that people struggle with and I really want to nail it. So I've just plugged in, the left-hand column is all the x values I'm going to use, and the right-hand column is it's going to calculate the square root of those x values for me. So 0, the answer is 0. Enter, I'll put a 1 in, the answer is 1. And you can see it graphing as we go those points. All right, so by now it's got an idea of what sequence I want, so it's going to put in the numbers for me. All right, so 2, square root of 2 is 1.41, square root of 3, square root of 4, which is a nice number, square root of 5, 6, 7, 8, 9, and we'll stop there because it's a nice number. All right, now, when you do the square root function, obviously the numbers that are not nice square numbers will have surd answers. You're not expected to know those, so what I would suggest you do if you're asked to graph them is to graph nice square numbers and then join everything else up with that curve that you can see appearing. And if you can't picture it, I'll turn it on, and there it is. All right, so it goes off into infinity as the x gets bigger. Now, we specifically wanted to have a look at a dilation factor. So let's use a dilation factor of 3. So I'll use 3 root x. Now this is going to calculate them for me. All right, so you can see straight away that there's been a change. It's almost like someone has grabbed here and stretched up. This 0, 0 has remained anchored, as you can see here. 0, even 0 times 3 is still 0. But every other number has been multiplied by 3. All right, so 2 by 3, 1 by 3, 3 by 3. Everything is now 3 times bigger. And the effect you can see on the graph is that the original point has now moved vertically upwards to 3 times bigger than what it was. All right, so this change is known as a dilation from the x-axis. All right, and it's because when you multiply a y value by a constant, so if you're looking here, the a value is out the front, which indicates that it's being multiplied after the square root's been done, it's then being multiplied by something else. You change it in the vertical direction. All right, so it's being pushed away from or closer to the x-axis. All right, now it is understandable that sure, these dots are also moving closer to the y-axis, aren't they? But you can see here the change. The change I've drawn here is a vertical line. So that indicates that the change is away from the x-axis, even though an effect is also that it's getting closer to the y-axis. All right, so you've got to keep that in mind, that there are double effects to all of these changes that can happen. The key thing is you need to pick out the one that's the most important. So because this 3 root x, the 3 root x is happening after the square root, it indicates it's in the y direction or away from or closer to the x-axis. So just like other equations, you've seen what happens when I put a big number in front of the a value. A good thing to remember would be that if I change that to a fraction, it would most likely push these values down towards the x-axis. All right, so keep that in mind, and again, we'll do more of that in future sets, but keep that in mind that if this a value is a whole number, it pushes it away from. If it's a fraction, it pushes it closer to.